There we go. How does that look, Doug?
It looks great, John.
Okay, so we'll start her up here. So, question 1, discuss 2 characteristics of water that are important to the brewing process. Well, I'm going to discuss all of these in detail, but there are 2 basic characteristics that I think address this question are the water quality, which is its cleanliness, and the mineral profile, which, believe me, we're going to get more into in a minute. Question 2, summarize 2 water treatment methods that brewers use to adjust and control the mash pH. Actually, they're more like 5, and these would be salt additions, acid additions, pre-boiling the water to precipitate temporary hardness, ion exchange to soften the water or strip out minerals, and then reverse osmosis, which more of you are familiar with, that you use to remove all the minerals from the water. Okay, so any 2 of those. Question 3, discuss how the mineral content of the water played a role in the development of 4 world beer styles. Well, the basis of this question comes down to the interaction of the residual alkalinity of the water and the grain bill for the beer in determining the mash pH. Now, if the mash pH is not ideal, you can have various problems. You can have poor conversion from denaturing the amylase enzymes, or you can have harsh bitterness and astringency as a result of high pH in the mash. So there's some issues there. Also, then you have the sulfate, chloride, and mineral structure characteristics of the water and how they affect the beer flavor. And once you've described those interactions of how water affects beer flavor, now you can describe the city and its water and the development of a particular beer style. So I want you to keep, as we go through these subjects, I want you to keep that structure in mind, that you're going to first talk about how the water affects the water and the grain bill determine the mash pH. Then you're going to talk about how sulfate, chloride, and minerals affect the flavors expressed by the beer. And then you're going to talk about a particular city and its beer style with regard to those parameters. All right, let's get back into some basics. Why do we as brewers adjust water? And we do it for 2 main reasons. We do it to improve beer yield, and that is we do it to create a better mash and thereby create more wort and a better wort. Once we have that better wort, now we can use that to create more and better beer. So by improving the water, we can improve our beer yield. We also do it to improve beer flavor, and we do it by those 3 items we just talked about. The flavor balance, that's sulfate and chloride, the flavor structure, that's total dissolved solids, and flavor expression, which is a function of beer pH, how the pH of the beer works to express the flavors of the beer to your palate. All right, so going back to question 1, water quality. Quality is the water's cleanliness. And you have 3 types of contaminants in your water that can affect your beer. Some are physical contaminants, such as sediment. You can have chemical contaminants, which can be anything from pesticides or industrial pollution, chromium-6, other chemical contaminants in the water. And you can also have biological contaminants, and those can be, bacteria such as E. coli, or parasites such as Cryptosporidium or something like that. And each of these are dealt with in similar ways. Filtration is always the first step. Use sediment filtration to get rid of any silt and excess silicates. Use carbon filtration to neutralize chemical contaminants. And then you use residual disinfection, such as chlorine and chloramine, to get rid of biological contaminants in the water. So your water quality is your first characteristic. Your second characteristic is the water source. The second characteristic of water quality is the water source. Where does that water come from? Because that will tell you a lot about what kinds of contaminants that water may have. If it's a surface water, that is lakes, rivers, streams, comes from runoff, that can be very low in minerals, dissolved minerals, but very high in organics. And organics are things such as algae, dead frogs, leaves, and so on, stuff like that. Groundwater, on the other hand, this comes from aquifers under the ground. It's often been underground for hundreds, if not thousands of years, and it typically has high degree of dissolved minerals in it and very low organics. So, as you know, many springs are drinkable, potable, coming right out of the ground. They're very clean in terms of organic contamination. So, water source is another good indicator of water quality. The mineral profile is the next characteristic of water. And of course, this is where we get to start talking about the chemistry. The mineral content of the water is the chemistry of the brewing water. And the water chemistry plus the malt chemistry equals our beer chemistry, which we measure as pH. Okay? That's a very important statement right there to understand. It helps. That statement is how you should be able to think about water and beer. It's water plus your malts equals your beer chemistry, which we measure as pH. Beer chemistry is responsible for beer flavor. And beer chemistry not only encompasses the pH, but also the mineral content of the beer, the calcium, magnesium, the alkalinity, sodium, chloride, sulfate. All of those things come together to define the chemistry of the beer and how that beer tastes to you. So it's important to understand that the mineral content of the water has a big effect on beer flavor because of that reaction. Water chemistry, malt chemistry, beer chemistry.
John, let me mention to everybody again, the polls are one of the things that give us insight into where you are. So far, for example, have you ever made water adjustments with your beer? So far, we have 43 votes that say yes, but 13 that say no.
Okay.
And on the pH chemistry question, the preponderance of people are saying a brief review, would be appreciated very strongly, 65%.
Okay.
And let's see, anything. I think those are the main questions that you're interested in at this point.
Yes.
So it looks like we're pretty good on people using brewing salts, but brief review on pH, cations, and ions would be appreciated.
Okay, we'll definitely do that.
And please continue.
Okay. So there's our mineral profile slide. So let's talk about how water affects beer flavor then. The residual alkalinity of the water, which I will explain in a minute, drives the mash pH in conjunction with your grain bill. Your mash pH drives your beer pH, and your beer pH drives the beer flavor expression. Generally, lower pH tends to focus and brighten the malt and hop flavors. By focus, I mean it kind of narrows them. Higher pH, on the other hand, tends to broaden malt and hop flavors. And this is especially, you can perceive it if you're drinking, say, a malty or a dark beer, like a porter that has like 2, 3, 4 specialty malts in it, a little higher beer pH in a dark beer like that tends to open up that malt character a little bit and allow you to taste each of the different specialty malts. So lower pH tends to focus malt flavors, higher pH tends to broaden malt flavors. Okay, that's beer pH flavor expression. Seasoning balance. This is the sulfite and chloride. We talk a lot about the sulfate to chloride ratio. We talk about the ratio because that's an easy concept to understand, but I want to impress on you at this point that it is not just the ratio, it is also the total concentrations of the sulfate and chloride. In other words, 40 parts per million to 10 parts per million sulfate to chloride will not taste the same as 400 to 100, even though the ratio is the same. Okay, what do these two ions do? Well, more sulfate tends to make that hop character a little drier and more assertive, but also makes that hop bitterness fade faster. So it makes it more aggressive. Lower sulfate that allows hop character to persist longer and makes the beer less dry. Chloride acts on the malt, both sodium and chloride really, but chloride particularly helps round out and increase the perception of sweetness of the malt. It makes that malt character a little rounder and fuller. Less chloride, doesn't do away with that. It just, literally sulfate and chloride are like salting your food. It's exactly the same effect. Your food has flavor, salt will enhance it. You can easily oversalt your food and you can easily undersalt your food. Same concepts here with sulfate, chloride, and beer. Okay. Now the amount of seasoning is what we refer to as mineral structure. And this is, as I was saying, the total amount of sulfate and chloride and sodium, and as well as calcium and bicarbonate. The total amount of minerals in the water is the total amount of seasoning that supports all the beer's flavors. And we refer to this as mineral structure. And so a water with a low amount of dissolved minerals would have a low structure. A water with a high amount of dissolved minerals would have a higher amount of structure to support those beer's flavors. Okay. Okay.
That timed that poorly?
Yeah, no worries. Yeah. No, I was just looking at some of the comments. So let me back up. I should have moved this particular slide a little higher up in the order. What is a mineral? Well, a mineral is any naturally occurring solid substance with a specific chemical composition, such as table salt, sodium chloride. And the minerals in water are typically dissolved salts, such as sodium chloride, calcium sulfate, magnesium sulfate, and calcium carbonate. Okay. Once minerals are dissolved in water, they dissociate into their separate ions. And so we talk about calcium ions, magnesium ions, sulfate, bicarbonate ions. And I apologize for those of you who don't remember your chemistry well. When we talk about minerals in water, we're really talking about dissolved minerals in water, which means we're really talking about the ions in the water. And we should say calcium ion, but we never do. We're lazy. We always just say calcium. What's the calcium in the water? What's the magnesium in the water? What's the sulfate in the water? But really, we are talking about ions, okay? Just want to clarify that. Cations are your positively charged ions, like your calcium and magnesium. Anions are negative ions, and that's your sulfate and bicarbonate, for example, also your chloride. If any of you are familiar with brewing software, water software such as Brew and Water or my own water spreadsheet, we talk about the electrical chemical charge balance. And what this is it's saying that anytime you dissolve a salt in water, the dissolved cations, their total charge must always equal the total negative charge of the anions. And so if you look at a water report and you add up the charges, it should come out to zero. They should cancel each other out. If they don't, that means that you're probably looking at a list of averages, and the average you see for the end of the year may not reflect what the actual concentration of a particular ion is during the year. Okay, that's why we talk about electric charge balance, is give us an understanding of how accurate a water test report may be. It should balance out to zero. And I explain all this better in How to Brew and in the water book. So forgive me if I'm leaving you a little bit hazy right now.
Now, this is great, John.
Okay.
It really is. And we're getting a lot of positive comments.
Oh, good. Okay. So let's talk some about the different minerals. We have minerals that in water that affect the pH, and those are calcium, magnesium, and the total alkalinity. Total alkalinity is actually a titration test where you measure the amount of acid needed to neutralize that alkalinity to a preset pH condition. Sorry. Bicarbonate ion is the primary alkalinity ion in potable water. That is, any water that you're getting out of the tap is probably going to be somewhere with a pH of somewhere between 7.5 and 9. Those are the typical pH range of potable water. And in that case, at those pH at that pH level, bicarbonate is going to be somewhere between 95 and 98% of the total alkalinity. Again, I explain this better in How to Brew and in the water book. But calcium, magnesium, bicarbonate are your pH ions. The ions that affect flavor and don't affect pH are sulfate, chloride, and sodium. Okay. When we talk about mineral concentrations in water, generally we say that 0 to 50 ppm is a low concentration. 50 to 100 is medium. 100 to 150 ppm is high. And over 150 ppm is a problem. The reason I mention these typical concentrations, as you look at the water profiles of various brewing cities, notice which ions are in low concentrations. Notice which ions are in high concentrations. So often I get questions from brewers asking me asking me about their water, and they send me a water report where everything in their water is less than 20 ppm. And I say, you have great brewing water, but it's easy to adjust. There's really no minerals in it to speak of. You can add salts, you can add gypsum, you can add calcium chloride to that water to build up any water profile you want. Other times I will have people send me their water report, and they'll have a total alkalinity that's like 300. And it's like, at that point, it's like, oh my God, that water is horrible to brew with. You need to either dilute it with distilled water or send it through reverse osmosis or something, because alkalinity over 150 ppm becomes a problem to treat. You have to look at acidification, you have to look at ion exchange and reverse osmosis to get those numbers down. So that's why I'm showing these mineral concentrations to help you put some boundaries around what you see on a water report. Okay, so going back to source water, Surface water, low in minerals, high in organics. We often use carbon filtration to remove these organic odors and flavors. Sometimes the odor is pond-like, and other times it's swimming pool-like, depending on what those organic odors are. Groundwater, on the other hand, is usually high in minerals and low in organics. Generally, the water tastes okay, smells okay, but in terms of brewing, we often need to reduce the alkalinity. And we can, do acidification, ion exchange, or reverse osmosis to do that. Okay. So typical brewing water source treatments. First off, you'd filter your source water. Filter it for particle filtration for silt, that's physical contaminants. Carbon filtration for organics, those are your chemical contaminants. The carbon filtration would also take care of a lot of those organic potential biological factors as well. Next, you would adjust the source water by adjusting the residual alkalinity of the water, and this is your calcium, magnesium, and alkalinity adjustments. You can also adjust the flavor balance by selecting which brewing salts that you use to do that, those calcium adjustments. You can manipulate your sulfate and chloride ratio. Okay, I see a question from Michael about the tables in Beersmith. Well, I'll try to get to that later towards the end of the talk, because I don't remember.
I'll make that a question.
Okay, I don't remember what those tables look like off the top of my head. They're probably similar to what I have. Okay, so what is water hardness? We talk about water hardness a lot. Hardness is simply the sum of the calcium and magnesium measured as calcium carbonate. You'll often on your water reports, you'll see a line that says total hardness as calcium carbonate. And this is a chemical equivalence of your calcium and magnesium. As brewers, we want calcium and magnesium in our water. It's good for yeast health, it's good for beer clarity, yeast flocculation, and so on. Water hardness helps us lower our mash pH to our target range. We talk about two types of hardness. We talk about permanent hardness, and this is calcium and magnesium that is dissolved from high solubility salts such as sulfates and chlorides. Calcium sulfate, calcium chloride. We talk about temporary hardness. This is calcium and magnesium that is dissolved from low solubility salts such as calcium carbonate and magnesium carbonate, otherwise known as limestone. Soft water is simply not hard, okay? It means that there are low concentrations of calcium and magnesium in the water when we say soft water. It doesn't tell us anything about the levels of the other ions in the water, particularly the alkalinity. You can have high alkalinity in water, but low hardness, okay? Soft water can be highly alkaline. What is alkalinity? Well, it is the sum of the carbonate species in the water that are dissolved from limestone. And in most tap water, with between a pH of 7.5 and 9, the alkalinity is roughly equal to the temporary hardness because, again, temporary hardness is calcium and magnesium that comes from dissolved limestone. So this is why brewing textbooks talk about getting rid of temporary hardness before you brew. And it's because we want to get rid of that alkalinity. We don't really want to get rid of the calcium and magnesium. And the reason we want to get rid of alkalinity is because it acts to buffer the lowering of the mash pH, which makes our beer less acidic but duller tasting, and in some cases more astringent. Okay, so what is residual alkalinity exactly? Well, it's the difference between the effects of the total alkalinity and the total hardness on mash pH. There's the equation right there. Total alkalinity equals residual alkalinity equals total alkalinity minus calcium plus half the magnesium divided by 3.5. And what we're doing there is we're saying that total alkalinity is going to act to raise mash pH. Calcium and magnesium are going to act to lower mash pH, and there's your net result. How does calcium magnesium react to lower mash pH, you ask? And this is the equation right here. This is going to be on the quiz later, so you may want to memorize this. What happens is you have calcium reacting with malt phosphates, also bicarbonate and water, to create calcium phosphate, which is a solid precipitate. You create carbon dioxide, you create water, and you create 2 hydrogen ions. Now, those 2 hydrogen ions are what act as one mechanism that acts to lower the mash pH from what the water pH had been down to our target of 5.2 to 5.6. Okay? So this is residual alkalinity. We're talking about the effect, the net effect of whether the water is going to act to raise mash pH with high alkalinity or lower mash pH through higher hardness, according to these equations. So, as an example, let's look at an example mash here. We have the distilled water mash pH of a base malt. If you take base malt, such as Pilsner malt or Pale Ale malt, and you mash it in distilled water, you would typically see a mash pH of somewhere between 5.6 and 6.0. 5.8 is your typical average. Okay, so let's see. So getting down to our target pH range of 5.2 to 5.6 is somewhat of a problem because our baseline mash pH is 5.8. The residual alkalinity of the water can either raise or lower that mash pH by about 1/10 for every 50 to 75 parts per million as calcium carbonate. Okay. If you have a negative value of residual alkalinity, that means there's more hardness than alkalinity in the water, and the water will help lower your mash pH. If you have a positive value of residual alkalinity, that means you have more alkalinity than hardness, and the net result is you will raise the mash pH from that baseline value. Okay? And about anywhere between 50 and 75 ppm seems to change that pH by about 1/10. Okay. So this is why we typically want to add hardness and remove alkalinity from our brewing water.
So John, let's look at those polls just to kind of see where we are there.
All right.
So again, we are brief review on chemistry and pH is still leading at 63.9%. And I think that's the main question we've got. So this is the level you're going through, kind of getting this review for us.
Yeah. How this all works together.
All right.
Okay.
If there are any other comments, put them there in the chat so we can get John to zero in if we miss something.
Okay.
Proceed, sir.
All right. Well, sulfate and chloride now. So as we said earlier, sulfate acts to accentuate the hop character of the beer. It makes that hop character drier and more assertive. Makes the beer character more drier and more assertive. It also shortens the dwell time of the bitterness on your tongue. If you drink an IPA that has a decent amount of sulfate in it, anywhere upwards of 100 ppm, you'll notice that hop bitterness hits the front of your tongue at the beginning of the sip, is very bitter, but then fades quickly after you swallow. It doesn't linger on the palate. If you have low levels of sulfate, that bitterness is going to linger longer on the palate. Sodium or chloride and sodium both act to make the malt character sweeter and rounder. And you can experience this when you're cooking in the kitchen. You're making something sweet, you add a little bit of salt to it, and it seems to make that dish much sweeter. It's the same exact chemistry at work in beer, okay? So this is how chloride and sodium increase that malt character, sweetness, and roundness. The ratio can, I say it can affect the flavor balance. That's not really true. This is seasoning. So you can accentuate the flavor balance, or you can not accentuate the flavor balance. You're not going to change it. Salt is not going to change the flavor of a dish. And putting in lots of chloride is not going to make an IPA very sweet and malty. It'll just make it taste minerally. You can only do so much with salt additions, is my point. But you can accentuate the flavor balance of the beer you have. And that's where sulfate and chloride additions and that ratio are useful. But if you have an IPA, having a sulfate to chloride ratio of roughly 4:1, as for example, makes for a nice, crisp, assertive, bitter beer. If you're brewing a Bock or a Munich Helles or something with, emphasizes more malt character, then you're going to want higher chloride than sulfate, something like, say, 50 ppm sulfate and 100 ppm chloride. That will help accentuate the malt character and of that beer, say, of a Munich Helles, and not have the sulfur, the hop character dominate what should otherwise be a nicely malty beer. So that's the action of sulfate and chloride. Mineral structure, total dissolved solids, light versus heavy seasoning. And let's look at these three beer styles: Bohemian Pilsner, German Pilsner, and Dortmunder Export. Now, I understand that the latest BJCP guidelines 2015, I'm not sure if they still identify these particular styles. I kind of go off the older 2008 guidelines, but bear with me. Bohemian Pilsner, a big malty beer, definitely bitter, but it's a big soft bitterness. The whole beer is softly rich, malty, and bitter, and balanced, okay? It is a smooth beer, no sharp edges, much like the Sierra Nevada Nooner we were just drinking. German Pilsner, and a German Pilsner such as, Hockershore or Beck's, or, what would pick a brand, tend to be a little more crisp, and a little more, the bitterness is a bit more assertive, with a little more hop forward character. So cleaner, drier finished. And that is the effect of a little bit more mineral in that water, giving those beers, that beer style, a little bit crisper flavor than the Bohemian Pilsner or Czech Pilsner. You go to Dortmunder Export, and here is a beer that's actually a smaller beer than the other two styles typically, but it doesn't taste like it. And it's because you have higher mineral character in the water that is better supporting all of those malt and hop flavors. And so it is a full-bodied beer. It is a rich beer, but it is actually a slightly smaller original gravity than the other styles, but it doesn't taste like it. If you look at the waters of these three cities, and there we go. There are, if you look at the total dissolved solids over there on the right, Pilsen 50, Munich 150, Dortmund 775. You can kind of see the order of magnitude increase in mineral content across these three waters. And again, looking at the sulfate, 8 to 18 to 330, for example. Much more assertive sulfate character in the Dortmund versus the Munich. Same with the chloride. So this is meant to be an illustration of how water mineral character can affect the beer style. These 3 beer styles have roughly the same kind of recipe: Pilsner malt, noble hops, lager yeast, but slightly different styles nonetheless, and water is a part of that. The water pH is not important. The water pH is not important. It's not important. It is actually the chemical equilibrium of the water. In other words, it's the balance between hardness and alkalinity. If you have a high water pH, such as 9, that simply means that there is more alkalinity than hardness in that water. It doesn't say how much more. 2 different waters can have the same water pH, but have very different mineral profiles. So this is why the water pH is not important. People always tell me, it's like, oh yeah, I've got bad brewing water, my pH is really high. Well, what are your mineral levels? Because you can have a pH of 9 with mineral levels all in the 20 ppm range. Yeah, it happens all the time. And that water is easily adjusted and by the malts in your mash. There's very little buffering in bicarbonate levels of 20 ppm, even though the water pH is 9. So this is why water pH is not important. We as brewers are interested in the chemical equilibrium of the mash, and the mash pH is dependent on the total concentrations of the minerals in the water. Okay. Let's talk about malt chemistry a little bit, because we've talked a bit about water chemistry. I'm going to talk a little bit about the malt chemistry, give you an idea of how these 2 factors come together to create the mash chemistry. Okay. So your malts, your specialty malts, are base malts that have been kilned or roasted to produce color, which we call melanoidins, and flavor compounds. These color and flavor compounds are a result of Maillard reactions, that is, non-enzymatic browning reactions that occur in food. These Maillard reactions also produce organic acids, such as acetic acid, and generally a higher color, in the malt means that malt is more acidic, has more of these melanoidin compounds, more flavor compounds, and as a result of that, more acid compounds as well. Okay, so generally a higher color in a specialty malt means that it's more acidic. There is, however, a transition from kilning to roasting about at temperatures of about 325 to 350 degrees Fahrenheit, or 165 to 175 degrees Celsius. And what happens, we think, is that these yellow-red melanoidins polymerize into brown melanoidins. Some of them pyrolyze, that is, they burn, they combine, and some of this acid boils off. And so we end up losing acidity. And so if you look at kilned malt acidity versus roasted malt acidity, I know we have said that darker is generally lower pH. However, your highest colored caramel malts have a higher acidity and buffering power than your roast malts, because the roasting process pyrolyzes and breaks down some of the buffers and acids that are in those caramel malts. So to put it another way, the grain bill for an imperial red ale would have higher acidity than the grain bill for an imperial Russian stout. Something to think about there.
Yeah, Lynn Howard's helped us with the styles there. 2015 Bohemian Pilsner is a 34B Czech premium pale lager.
Yes.
And the German Pils is 5D German Pils. Dortmunder Export is a 5C. Thank you, Lynn. I was going to look it up, but I probably fall asleep at the switch like I have a couple of times here.
Okay, well, let's move on. My son told me a joke the other day. He said, what's the definition of a professor? And it's like, I don't know. It's like somebody who's talking while you're sleeping. So
I like that. I had a few of those professors.
Yeah. So water plus grist equals your mash pH. Let's assume that our target mash pH is 5.4. Our base malt has a distilled water mash pH of 5.8. It is alkaline with regards to our pH target of 5.4. And so all of that base malt needs to come down to our target mash pH of 5.4. The specialty malts, on the other hand, those typically have a distilled water mash pH of like 4.6, for example. Sometimes they're 4.6, 4.7, 4.8, 4.5. I'm just saying 4.6, for example. In other words, they are acidic with regard to our target mash pH. Their pH needs to come up. The residual alkalinity of the water can be either positive or negative, and so it can help or hinder us reaching our target mash pH. And in fact, you could create a grain bill that would exactly hit your target mash pH simply by doing a mass balance of your alkaline base malt plus your acidic specialty malts plus the residual alkalinity of your water. And in fact, if you think about these three quantities as the points of a triangle and the links of the sides of that triangle, the balance point of that triangle would be the mash pH. So that's a good way to think about how these three factors interact. You have your alkaline base malt quantity, you have your specialty malt acid quantity, and then you have your residual alkalinity. And the way those three come together into a triangle, the balance point of that triangle, that's your mash pH.
John, is the triangle perfectly proportioned, or does one affect the other a little more than the other?
It's a concept.
Okay.
So
it's like right, three legs on a chair.
Yeah. If you take any three lines and make a triangle, if you take a piece of paper, cut out a triangle out of it, find that balance point where the mass of that piece of paper balances on the pencil. That's the analogy I'm making to how the alkalinity of the base malt, the acidity of the specialty malt, and the residual alkalinity of the water combine to create the mash pH.
That was a three-legged stool, not a chair.
Right. There you go. Right. Anyway, another important concept to understand is the mash pH sets up the beer pH. So if you look at this diagram, you can see we start out with our mash in our 5.2 to 5.6 range over here. As we conduct that hour-long mash, those reactions are still happening in the mash. The calcium's combining with the malt phosphates, generating those hydrogen ions, and during the mash, that mash pH will continually fall. Typically, you'll see a drop of about 0.2 pH units during the mash. Sometimes it's 0.1, sometimes it may be 0.3, typically 0.2. Now, at the end of the mash, we go to the boil. During the boil, we're seeing protein coagulation. We're adding hops, which are alpha acids. We're boiling off water, which is changing the concentration of those buffering compounds. Typically, we see a further reduction of about 0.3 in pH during the boil. And so that's here. Now we go into fermentation. During fermentation, the yeast are taking in amino acids. They're, producing carbon dioxide. They're excreting protons. They also have a big effect on pH. They tend to change the pH by about a half. So this is how we get from our mash pH down to our typical beer pH range of about 4.0 to 4.6 for most beers. Lagers
John, that's
tend to
a
be.
phenomenal chart. I
Thank
love
you.
that chart.
Thank
I've never
you.
seen that one. That's a great one.
It's supposed to be in How to Brew. I forget if it's in there or not.
Well, you know, mine's an old copy.
Okay, yeah. If you don't have the new one, it's the yellow book, which I've got a sticker on the cover, but and tags, you know. But this, the new one, has up-to-date water discussion in it. So there's mash pH to beer pH. So let's review how water affects beer flavor. You have your residual alkalinity, which drives the mash pH. The mash pH drives the beer pH. The beer pH drives beer flavor expression. You know, I've often used my spaghetti sauce example. If you go to the grocery store and you buy a commercial spaghetti sauce, it's often, sweet, kind of rich, tomatoey. The kids love it, but it's not a very interesting spaghetti sauce. Whereas if you go to the local Italian restaurant, the tomatoes may have been fresh picked that morning. They've been gently squeezed into the kettle by nuns, creating a very bright, acidic tomato sauce. Bright acidity, not a lot of complexity in that tomato sauce. To get the best spaghetti sauce, you need a compromise of those two extremes. You need a pH that's somewhere in the middle, where you have a balance of bright acidity and complexity. And this is the same way we need to think about our beer and our beer pH. So lower beer pH tends to brighten those malt and hop flavors, but focus them. Higher pH tends to broaden those malt and hop flavors. And if you go too far in the high pH, then you can run into harsh flavors, coarse flavors, and astringency. Okay. Next, we talk about the seasoning balance. Are we trying to accentuate the hop character of the beer for a hoppy beer, or accentuate the malt character of the beer for a malty beer? Or are we going to balance the sulfate and chloride so that we end up with a more balanced beer flavor? Again, it's seasoning. It is not going to change the flavor of the beer. It is simply going to accentuate the flavors that are already there. We also talk about the amount of seasoning, that is the mineral structure of that the ions in the water impart to the beer. Low mineral water, distilled water, reverse osmosis water, no minerals, very little structure, kind of a watery beer is the result. High mineral water, Burton-on-Trent, for example, lots of minerals, Dortmunder Export or Dortmund water, you tend to get very robust beer flavors. Okay. Again, those are the general relationships.
John, you're getting a lot of positive comments on the spaghetti sauce analogy.
Oh, good.
I knew you would. We talked about that last night. That is just one of your best.
Good.
Almost as good as the brew cube.
Well, that's up next. So
I didn't even realize that. Perfect timing.
So this is the brew cube, and I came up with this a couple of years ago, just before the most recent edition of How to Brew went to press. I was talking with a homebrewing club in Athens, Greece, and trying to come up with a better metaphor or analogy to explain how these water parameters relate to style parameters. And I came up with this Rubik's Cube kind of idea. What we're doing with the brew cube is we're saying we're going to define our beer style by 3 parameters. We're going to define it by flavor balance. We're going to describe it by color. And we're going to describe it by structure. And from that, we look at the water that complements that beer style. So for beer color, we talk about residual alkalinity. For pale beers, we want negative residual alkalinity. For amber beers, we want near zero residual alkalinity. And for dark beers, we want positive residual alkalinity. That way, these dark acidic malts, the specialty malts, balance the alkaline buffering capability of the water. Okay, and we end up with our target mash pH range. For 0 residual alkalinity, light, amber colored specialty malts are going to provide enough acidity to help bring us down to our target range. For pale beers with, really no, we're essentially an alkaline grain bill, we're going to use the residual alkalinity of the water, the extra hardness, to help us hit our target range. So that's how beer color and residual alkalinity relate. We go to flavor balance, malty, balanced, or hoppy. This is our sulfate to chloride ratio over here. So you follow these around. If we want a hoppy beer, we'd be looking for a sulfate to chloride ratio of roughly 4:1, for example. Maybe 2:1, it may be 6:1, but whatever. If we're looking for a balanced beer flavor, then we're looking for more of a 1:1 sulfate to chloride ratio. Maybe that's 50-50, maybe that's 100-100, whatever, more balanced ratio. If we're looking for a malty beer, then we'd be looking for a water that has more of a 1/2 sulfate to chloride ratio. And finally, beer structure. Is this a soft beer like a Pilsner, or a medium beer like, what's a good example of a medium beer? Well, most anything really. I think most beers, if they're not soft, they tend to be medium. There are very few firm beers. The couple I've tasted would be, a Dortmunder export style, such as Barley Forge's Grandpa Tractor, or some of your Burton ales. Those can be quite firm. Worthington White Shield, for example, very firm mineral character in those beers. And beer structure is of course dependent on your total dissolved solids, your total sulfate and chloride concentrations, but it scales most effectively with your calcium concentration, because and if you understand water, you'll understand that generally calcium is going to be between 20 to 40 ppm in most water supplies, or lower. As you build the calcium to get you up to that recommended 50 ppm minimum for good beer clarity and good fermentation performance, you're adding calcium salts, you're adding calcium sulfate or calcium chloride, or magnesium sulfite, magnesium chloride, and so on. You're essentially adding to that total dissolved solids number. As you're trying to, improve your residual alkalinity and increasing that calcium level up to 100 ppm, again, you're adding more salts. So you really are increasing that total dissolved solids, and that's why I use calcium as the corresponding scale for beer structure on the beer cube. I talk about it being total dissolved solids, but it's really directly proportional to your total calcium, your final calcium concentration in your water.
So, John, where would a complex beer, like a Russian Imperial Stout or a barley wine, where would that fit on this? Because those are really complex beers.
Yeah. Well, okay, so let's say a Russian Imperial Stout, good example. It's a dark beer style. Okay, so we're going to go down here to our beer color, and we're going to say we want a residual alkalinity of roughly 100 parts per million as calcium carbonate. That's our residual alkalinity target. Now, do we want that Russian Imperial Stout to have a soft character? Probably not. Probably looking for something a little heartier. Probably a medium. Maybe not a firm. Firm maybe, and a Russian Imperial Stout may be too heavy. So we'll assume we want, for at least first try, we want a medium beer structure. And that means we're going to want a water chemistry with about 100 ppm of calcium in it. So right now we've got a water that has plus 100 residual alkalinity and about 100 ppm of calcium. Russian Imperial Stout, do we want it to be super malty, or do we want it to be a little more balanced? That's up to you as the brewer. But, there again, here we're looking at, we want something with a little more chloride than sulfate, or more balanced 1-to-1 chloride, sulfate to chloride. Those are your water parameters that you're targeting. So you're saying, okay, dark, soft, balanced. We're looking at a cube that's essentially, in the middle bottom of that cube there. And that's it. But you can see how
it would be really cool to kind of go through all the beer styles on the cube. I know we don't have time tonight, but
right,
that would be very.
There's 27 combinations, according to the cube. I think maybe, like I say, very few actual beers are going to fall in this firm category. Very few beers are going to, be both high calcium and high alkalinity. So I think of those 27 combinations, I'm saying maybe half of them are going to see real use in terms of an actual beer style. But this is what I want you to understand, looking at the brew cube, is how beer style parameters relate to water parameters. And understanding water and water adjustment doesn't have to get any more complicated than this, especially when you start talking about classic beer styles and classic beer cities and the water that are used to make them. Dortmund or export, firm beer, pale, probably balanced. And so we're looking at, this cube here in terms of the water we want. We want something that has 150 calcium and kind of a 1-to-1 sulfate to chloride ratio. Okay. And negative residual alkalinity. That's how you understand the water that fits that beer style. These are how these things relate. And it's a general relationship. There's no absolute laws here. Okay. So that's the brew cube. So again, effective beer pH on flavor in general, a lower beer pH, something in the 4 to 4.4 range or 4.3 range, that's going to tend to focus and brighten those malt and hop flavors. Better for your single malt pale beers. In general, a higher beer pH, 4.3 to 4.6, is going to tend to open up and broaden those malt and hop flavors. Generally better for your multiple malt dark beers, higher pH. A amber colored beer, something like an amber pale ale or an amber lager, something with some both malt and hop flavor. You're going to probably, or maybe just one specialty malt, you're probably going to want something, a pH of, like 5.4 right in the middle.
John, I just got a little bit of a feel from our audience on how we're doing time-wise, because we're into a solid hour now.
Right.
And it looks like we're getting some very encouraging response there. Doug Valden says, brew on. Mike Brennan says, this is outstanding information. I'm not going anywhere. Steve Morgan says, keep going. Christopher Riley says, keep going. So if you're game, we're going to hang in there, even though we hadn't gotten to the questions yet. Are you going to hang in there with us?
I think I just need to go sparge quickly.
That'll work.
So give me 2 minutes and we'll come back. And we'll get into question 2.
That sounds great.
Okay, be right back.
Okay. So good. Maybe there might be some other folks that may be needing a bio break, and we'll keep this going. Steve Morgan says beer refill time. I like that. I am very interested in your feedback. We've got in our units that we've figured out, I think there's like 12 sections of the BJCP written that I'm trying to get speakers for each one of them. and I would appreciate your help. John was willing to volunteer. As I mentioned, we got Stan Hieronymus on Wednesday. Stan has really been working on this. And then John Mallett is going to help us with malts at the end of the month. None of those have gone live yet. I've given the folks in the webinar kind of an early peek at the Stan Hieronymus information. See, Jamil, I have contacted Jamil. I have not heard from him yet. So if anybody has a little pressure they can exert on Jamil, that would be great. He's usually pretty good about responding, but I asked him to do something this time. So that would be great to speak up for the benefit of this. I've got the word out to a few other folks, and so we're trying to twist some arms, but it really takes your help. You know, what they're responding to is those of you that are in our study group, and I would encourage you to be in one or the other. That helps me justify to them. We're up to almost 300 in the 201 group, and we're almost at 100 in the 101 group, and I think that will actually exceed the 201 group eventually, but it only started 10 days ago. So, you know, when I put in these that I'm looking for polls, you know, they're interested in knowing who the audience is. Christopher Riley asked about contributing. I do appreciate. I'll pop that up. I feel really awkward doing that, but it does help support it, and because it is totally self-funded, so I will pop that up again. This just the webinar platform by itself is $90 a month. So, but you know, we're getting some speakers in, and it's worth it. And gosh, just for the privilege for being with you folks and in a part of the study group, and you know, getting the chance to spend a little time with John Pallmer. I think any of us would spend that kind of money to spend some time with John. So, John, we've
anyway.
We've been kind of twisting the arm to see if anybody knows some other speakers to speak on the other topics. And Jamil was one of the names that came up. You know, can you twist Jamil's arm? Tell him you did this, and he needs to step up to the plate.
I'd be happy to. Yeah.
All right. Well, I've got an email into him. So
okay.
But one from you would be immensely helpful.
I'll do that. All right. Let's move on to question 2. I know we've covered a lot of material over the past hour. And the reason is that all of that material really feeds the answers to these questions on the exam. So let's talk about question 2 now, adjusting water to adjust mash pH. What we're going to do is adjust the residual alkalinity to adjust the mash pH, all else being equal for the same grain bill. You have 2 main options. You can either add hardness with salt additions, or you can reduce the alkalinity of the water with acid additions. And that can be either lactic acid, phosphoric acid, hydrochloric acid, or citric acid too. Other options are pre-boiling the water to precipitate the temporary hardness and alkalinity from the water. You can also do softening, ion exchange, to reduce the hardness or alkalinity, or both. You can do reverse osmosis on the water to filter all the ions out. All of these things are very effective methods for adjusting the water to help you to adjust and control your mash pH. Okay. So that was basically the answer to question 2. How do you name 2 methods that brewers use to adjust their water to adjust and control the mash pH? It could be adding hardness and reducing alkalinity, salt additions, acid additions, or it could be pre-boiling, ion exchange, or reverse osmosis. Those are other options as well. To pick any 2 of the 5 to discuss. And a good, well, I'll go into the final answer later.
Yeah, let me add one thing, John. I know we're not quite to the end, but we're getting close, and we have 29 questions. So let me just let everybody know, everybody has one vote on the questions. And I think we're going to be hard pressed to keep John through 29 questions. So if you'll look on the right, we've already got some votes for the questions, but make an effort to vote up instead of just adding another question. Vote up a question that's particularly important to you, because I suspect if we get a dozen of these questions, it will be amazing.
It'll take them another half hour.
Yeah. Maybe we get John to do another webinar and he can answer the rest of them, but at least for tonight. So please take some time and vote those up. So okay. I'll give you back the screen, John. Sorry.
Okay. Let's move on to question 3, which says, discuss how the water influenced the development of classic beer styles, 4 classic beer styles. Okay. So recipe development, style development starts with the mash. The better the mash works, the better the beer will work. And it's important to understand that pH is a modern concept. It's a modern tool. It was only invented in 1920. So 200 years ago, how did a brewer develop a new beer style? Or what did they use? Well, they used their tongue, they used their palate, they tasted the beer, they looked at the results of their mash, and it's like, hey, the mash didn't work. I didn't get much sugar out of my mash. So even though they didn't have a pH meter, very often they didn't have a hydrometer or a thermometer even, 300 years ago, 400 years ago, they had their senses. They could taste the beer, they could taste the wort, and those tools help them zero in on what worked and what didn't. So keep that concept in mind as you're thinking about how water and grain bill interacted to create a classic beer style. The better the mash worked, the better the beer is going to work. So therefore, the residual alkalinity of their water, their source water that they started out with, probably drove that initial grain bill. If their water had high residual alkalinity, they are going to need more specialty malts, more dark malts, brown malts, that would balance the alkalinity of that water with their acidity and achieve a good mash and good conversion. And that's going to determine whether that resulting beer style was pale, amber, or dark. Okay. Water adjustment has been going on for thousands of years in brewing. I kid you not. And it can be changing the water source. It can be salt additions. It could be natural acid additions through the use of lactic acid or acid malts, dark and roast malts, like I was saying. All of these things can adjust that mash pH. When it comes to adding hardness and reducing alkalinity, those processes were typically done to facilitate paler beer styles. And this is where the science of Burtonization came into play. They knew that, in the mid 1700s on up through the mid 1800s, that the beers of the Burton region had a crisper finish. They had higher yield. They had, good beer properties compared to other regions around the UK. And so they analyzed that water with the science of the time, determined what the amount of calcium was, the amount of sulfate. And you can read about this in Mitch Steele's IPA book. Very, very good read. And it was that science, that technology of how to manipulate beer and beer flavor that led to the creation of Pilsner beer in Pilsen around 1840. I had the privilege of talking with Dr. Ludwig Narcissus of Weinstefan and the Technical University of Munich a couple years ago. And I asked them this very question, how did the Pilsen brewers obtain good mash pH with such low mineral water? And he said, oh, they added salts. And I said, they did? And he goes, yes, they added salts. This was Burtonization. This was when this was science. And so the addition of calcium salts helped them manipulate their mash pH, even though pH won't be invented for another 75 years at that point. But, they were able to add these salts to their water and get and create a paler beer and a brighter beer than what they had previously achieved. So that was a real revelation to me, and it may be to some of you as well, that, Pilsner beer was created with this very soft water, but also with the addition of brewing salts, and not tons of salts.
There's really a lot of misinformation out there, John. Because,
there really is, and a lot of it has been romanticized and speculated, and all those speculations are repeated, and it takes actual historians and digging into the archives and asking people that are much closer to that region. Dr. Narcissus he's a wonderful man. He's a brewing professor. He's about 93 years old at this point. But he, Germany is just right over the border from the Czech Republic, maybe all of 50 miles away. They have access to records going back hundreds of years that documented how all of these beers were created and brewed. And so it's a matter of just finding the facts.
It goes back to this: brewing is an art. It really is an art, and it isn't just a matter of throwing together the materials in a particular region and it turns out to be a good beer style. Right. That's like saying you get a bucket of paint and throw it together and you'll have a painting.
Yeah, no. And it's so wonderful to realize how much of the science of modern civilization had its basis in brewing. Temperature, hydrometers, gravity, pH, cellular molecular biology. All of these things had their starts, at least in part, in the brewing industry, as brewers tried better to understand what made beer work. So it's a beautiful thing. Moving on.
Gary Fuller says, break down the dogma. Reminds me of Denny's breakdown of things we know to be true that aren't.
Right. So anyway, so we're talking here about, mash pH, better mash, and so on. Now we go on to the sulfate, chloride, and sodium concentrations in the source water of the city probably affected the flavor balance that we like in the style, whether that particular style happens to be malty, hoppy, or balanced. Okay. Again, the style may start out with that brewing, that local groundwater, that local water source that we see quoted everywhere, like I quote in How to Brew. But we're brewers. We adjust the water to improve the beer. So, just because, the sulfate, chloride, and sodium concentrations start out that way doesn't necessarily mean that's how that beer has been brewed ever after, because usually that's not the case. We've adjusted it. The minerals, of course, are the seasoning for the beer and the structure for the flavors. More minerals equals more structure, more robust flavors. So when you're talking about Dortmund and Dortmunder Export, you can talk about having robust flavors compared to Pilsen, Pilsner beer, similar recipes, Pilsner malt, noble hops, lager yeast, softer flavors, more robust flavors, less minerals, more minerals. Okay? And that leads right into the cities. So let's talk about Pilsner beer. The water has low levels of all minerals, low alkalinity, low hardness, low residual alkalinity, and low structures. And In the describing the beer, soft malt and hop flavors, the brewers added salts, and I said all that already. Irish Stout, Dublin. The water there in Dublin, the groundwater I should specify, has very high hardness, high alkalinity, high residual alkalinity. The sodium, chloride, and sulfate are relatively low. So what we have is a high alkalinity water, medium mineral structure, and unassertive flavors from the low sodium, chloride, and sulfate. This helps to produce a dry, roasty beer with good body, but without astringency and without any harsh flavors. You have soft bitterness. You have a smooth roast malt profile, not a harsh acrid malt profile. High drinkability. So the beer properties are a result of these water properties, at least in part. Dortmunder export lager. The water has high hardness, high alkalinity, low residual alkalinity, high sulfate, high chloride, low sodium. So 3:1 sulfate to chloride ratio, firm mineral structure. Water as is suitable for amber beers. You get good mash pH with an amber malt grain bill. And the water provides lots of support for those malt and hop flavors. Nice dry beer finish character. It tastes bigger and drier than a Pilsner, and that's due to that mineral structure. The sodium chloride help bring out, round out the malt character, and the high sulfate dries out the finish of the beer. Any questions, Doug?
Yeah, a lot of really just positive comments on
good.
How helpful this is, and I know we're a little bit silent, and it's really just we're all soaking this in, because it's for me anyway. It's kind of like, wow, I finally understand this stuff. I mean,
good.
You're making it. Al Boyce said this is the toughest question in the BJCP written exam, and you're. Well, I can't say you've made it easy, but you have really clarified things for at least me, and I think a lot of other people.
Well, good, because that's what I'm here for. That's my hope, to be able to teach this stuff accurately. All right. Well, let's talk about Vienna. Vienna's a little different. Medium calcium, high alkalinity, high residual alkalinity. Low sodium chloride, medium sulfate, medium mineral structure. So the water of Vienna is somewhat similar to Dortmund, but it lacks the calcium levels to balance out the carbonates. So essentially, when we could achieve mash pH with the Dortmund water, we have less calcium with Vienna. We need more specialty malts to achieve a good mash pH, and therefore your Vienna beer color is darker than your Dortmund beer color. Okay, and this is where the red amber lagers would come from. If they had tried in Vienna to duplicate the export style, but they were having harsher flavors in their beer, duller malt flavors, higher bitterness, and it was because of the lack of calcium. So adding more specialty malt help bring that pH down and reduce the astringency, brightened and focused those malt and hop flavors, and the Vienna lager style was born. Munich, medium calcium again, high alkalinity, high residual alkalinity, higher than Vienna. Low sodium and chloride, low sulfate, as opposed to higher sulfate. Medium mineral structure, so more alkalinity than Vienna, and therefore higher residual alkalinity. And so what you have as a result of that water is a generally darker, maltier beer. More malt helps balance the alkalinity of the water, helps neutralize it, helps you hit that 5.2 to 5.6 mash pH range. And the relatively low sulfate content provides for mellow hop character, mellow bitterness that lets that malt flavor dominate the beer rather than balancing it, as more of a pale ale, for example. Pre-boiling of the water allowed the development of some of the paler beer styles like Munich Helles. Moving on to London, medium calcium, low magnesium, high alkalinity, medium residual alkalinity. So again, we're kind of more with the medium residual alkalinity, we're into that dark amber to brown color range for equivalence on the beer cube. Relatively low levels of sodium, chloride, and sulfate, although not as low as Munich. Medium mineral structure. So I think here in the United States especially, and maybe in South America as well, we have this perception of the United Kingdom and London being all the same thing, as opposed to London, Edinburgh, and Dublin, being really separate, very separate regions. Turns out London is very separate from Burton-on-Trent. There's a good distance and different watersheds between them. But it's so easy here on this side of the world to just kind of lump it all together. Interesting to understand that the Thames River in London is brackish. It is a tidal river. And so the water is half salty in that river. And it's not very suitable for brewing. So the brewers there in London were brewing from the groundwater. And that groundwater had higher bicarbonate, that high alkalinity, medium residual alkalinity, and that's why they were able to brew their beers with brown malts and dark malts that neutralize that alkalinity. And going back to, if you look at the water book, I have a little bit of the story there. Again, Mitch Steele covers it in the IPA book. The brewers in the UK were very, they had scientific societies that talked about these things and documented it, and they investigated how much boiling was necessary to precipitate all the temporary hardness in the water. And then they determined it took about a good half hour of rapid boiling of the water to really drive out all the carbon dioxide and precipitate all the temporary hardness. They were actively adjusting water, 200 and 300 years ago. So wow. 300 and 400 years ago even. So, and you can Google some of these documents. They're available on the internet.
I'm fascinated with your brew cube. I wonder if you could color the cube, the sub cube of one of your cubes, and put that on the slide as kind of a reference point.
Yeah.
Would that actually work? Because it just almost seems like it tells a pictorial version of it.
Yeah. Well, and if you look in the new version of How to Brew in the recipe section, I talk about beer cube settings, pale, amber, dark, soft, firm, and so on the recipes. If you look on the brew cube, say between London, Munich, they would really have like the same cube space because of the ranges. Okay. These ranges would overlap. Of course, the beers are slightly different.
John, one thing, we're probably down to less than 15 minutes, and they literally will cut us off at 2 hours.
Okay. I have 3 more slides.
Yeah.
So let's rush through these and we'll get to the questions.
Okay.
Okay, so there's London. And these will be available for your review later. Edinburgh, Scotland, high calcium, low magnesium, high alkalinity, high residual alkalinity, high sulfate, medium chloride. Water that is not that much different from some of the other waters, but they brewed different beer with it. And part of it is due to economic considerations. Hops were expensive. Specialty malts were expensive. But they tended to brew darker beers, maltier beers, as a way to work with the water and achieve beers with very high drinkability. The beers were sweet but dry finish, very drinkable. Tended to be low, most of them tend to be low gravity, or your shilling ales tend to be fairly low gravity. But the water and the type of beer gave it some body, gave it some real nice drinkability. So very interesting story there with Scottish ale. Burton-on-Trent, we talked about a little bit about. Very high mineral groundwater. If you look at the numbers, and either on Brewing Water and How to Brew, the water is practically, you could practically build a house with it. It's so high in minerals. And as Mitch Steele explains in his IPA book, the brewers were brewing from wells that were placed next to the Trent River, and so the water they were brewing with was actually a mix of the high mineral groundwater and the low mineral river water, and so the actual mineral levels that they actually brewed with are probably half of the quoted groundwater values. We don't have good data on that today, but be that as it may, again, near zero residual alkalinity. So you're able to achieve mash pH with paler malts compared to the medium residual alkalinity of London and its brown ales and porters. High level of sulfate and low level of sodium produce a clean, assertive hop bitterness. Burton ales are drier, crisper, and more bitter than London ales as a result. So that being said, you had asked for my 2 cents of how I would answer these questions. So here are my answers. These next three slides are my answers. So question 1, discuss 2 characteristics of water that are important for the brewing process. And I would say 2 characteristics of the water that are important for the brewing process are water quality and mineral content. Water quality is the cleanliness of the water. Water can contain physical contaminants, chemical contaminants, and biological contaminants. These need to be filtered out of the water before use so they don't cause off flavors or other harmful effects in the beer. The mineral content of the water affects the mash pH and flavor of the beer. Calcium and magnesium react with malt phosphates to lower mash pH and water alkalinity. Principally bicarbonate buffers this reaction, essentially raising mash pH from the target range of 5.2 to 5.6. I know that's a very technical answer to the question, but that's how I would do it. And then I go on to say that sodium chloride and sulfate act as seasoning. Sodium chloride enhances the malt character, making it sweeter and rounder. Sulfate enhances the hop character, accentuating sulfur compounds in the aroma and making the bitterness more assertive and the finish drier. So there's my answer to question 1.
Oh, that is so good. Keep going.
Question
I
2.
Run out of time.
Summarize 2 water treatment methods brewers use to adjust and control the pH of the mash. Brewers can adjust the mash pH by adding hardness by salt addition or reducing alkalinity by acid addition. Both of these adjustments are done to the brewing water, although the timing of the adjustment can be at multiple points, either to the hot liquor tank, the mash tun, or both. Salt additions of calcium chloride, calcium sulfate, or magnesium sulfate can add hardness to the water, which acts to precipitate calcium or magnesium phosphate and release hydrogen ions, lowering the pH. Acid additions to the water will reduce carbonate and bicarbonate to carbon dioxide, which can be vented from the water and will reduce the alkalinity, thereby reducing mash pH. Another option for reducing alkalinity is to use reverse osmosis to strip most of the ions from the water and then build the water back up to brewing specification with the use of brewing salts. So that's really, there's almost 3 answers instead of 2, or 3 methods instead of 2 methods there. But I think that's a very thorough answer to question 2. Didn't take a whole lot of space.
Yeah, but how good it is. I won't slow you down. Keep going. I don't run out of time.
My answer to question 3, this is a 2-pager. Discuss how the mineral content of the water played a role in the development of the 4 world beer styles. Well, again, going back a couple slides, talk about how the alkalinity, the residual alkalinity of the water affects mash pH and grain bill. Grain bill, residual alkalinity, triangle, balance point, mash pH, that concept. In Dublin, the high alkalinity groundwater necessitated the use of brown and roast malts to supply the acidity to counteract the buffering of the water to reach the mash pH of 5.2 to 5.6. The high bicarbonate of Dublin would typically result in a higher, coarser bitterness. The reason the hop bitterness in Irish Stout is not assertive is that the lower boil pH due to the roast malts versus a higher boil pH, and B, relatively low levels of sulfate, creating a hearty beer without an assertive bitterness. So again, the water, high bicarbonate, low sulfate, bit dark beer, not terribly assertive bitterness. In Dortmund, the high hardness and high alkalinity balance to a low level of residual alkalinity, when I say about 20 ppm, allowing for sufficiently low and stable mash pH with pale colored malts. The sulfate, chloride, and sodium levels are fairly high. This results in a pale, full flavored beer, similar to Czech Pilsner and German Pils, but at a lower original gravity and drier finish than, say, Munich Helles style from Bavaria. Just to throw another beer style in there.
Wow.
Third beer in Vienna. The water does not have as much hardness as Dortmund and has lower levels of sulfate, chloride, and sodium. The alkalinity is similar. The result is that more specialty malts are needed to achieve a sufficiently low and stable mash pH and good conversion, and the beer is darker than Dortmund or Export with a softer, rounder finish, probably due to less sulfate. London water is similar to Vienna water in all ion levels: medium calcium, high alkalinity, medium residual alkalinity, and generally low levels of sodium, chloride, and sulfate. The beer color of porter is similar to Vienna lager, being a dark amber to brown due to the early use of brown malts for the style. The brown malts counteracted the alkaline water buffering to achieve the good mash pH. After the invention of the hydrometer, the low yield of brown malts caused the switch to higher yielding paler base malts plus specialty malts to achieve the same color and mash conditions. I kind of drifted off on a tangent there. You don't have to, but again, the purpose of the question is to demonstrate your knowledge of how water impacts recipe development and beer style development and what factors are changed. And so, as I said at the very beginning, residual alkalinity of the water directly affects your malt choices for the grain bill that you work with, because the end result of those two is, of course, your mash pH. And if the mash pH is good, you have a good beer. If the mash pH is bad, you're trying again until you get a good beer.
John, I think we've been drinking from a fire hose, but you've got to answer yourself the dominant question in the chat right now, and that is, first of all, are you going to share this PowerPoint?
Yes,
because everybody's been trying to take screenshots with their camera.
Okay, yeah, I've sent the PDF of this presentation to Doug, and you can distribute it to everyone. I've also talked to the BJCP judges and officials, and they are incorporating a lot of what you've seen today into a new water study guide. So I think they have the same goal as you do, of course, is better understanding of how water affects beer. And so they are in the process of updating the water study guide to incorporate some of these ideas.
Well, thank you, John. So just quickly, we've got a few questions. We'll take what's at the top. So again, if you want to vote and you hadn't used your one vote, I think we've got maybe 8 minutes before we get cut off hard. So John will go through the questions. I think you've really covered the first one, have you not?
Yes. I don't have here. I got to grab the questions.
Oh, I'll read it. It was summarized the two methods. It was question 2, I think.
Right. So, right. I've done those.
Yeah, so we could skip that. Second question is just seem mysterious and difficult to know. When you, anytime somebody votes, it pushes them around. So water adjustments seem just mysterious and difficult to know. When you have the right amount, you've described it like spices for cooking, but you can add those to taste. Can you do the same with water adjustments? Can you calibrate your palate by knowing how to add adjustments, maybe by taste, a little bit like cooking?
Yes, you can. Takes trial and error, though. And conversely, I would say that even if you take a commercial beer and try adding, baking soda or calcium sulfate to it to see what the effect of more sulfate would be on this particular beer, or more bicarbonate on this beer, it takes a lot more when you're doctoring a beer like that to taste a flavor difference. I added some and then did a triangle test, kind of spinning the table so I didn't know which cup was which, and I had a hard time picking out the different beer. Even after I'd added a significant amount of ion to, say, sulfate, I added like 150 ppm equivalent sulfate to one of the beers. Had a hard time discerning that in beer by doctoring the beer. But water adjustments are mysterious. The first priority is your mash pH. If your mash pH is in the right range, you will make good beer. If after that you can look at your mineral levels and adjust your sulfate and chloride to accentuate, to help that beer style, you will take that good beer and make it great. And the best way to do that is with brewing software like Beersmith or Brewer's Friend or Brewing Water or My Spreadsheet. Something that helps you calculate exactly how many grams of salt to add to the water to achieve these mineral levels in the, somewhere between 50 and 150 ppm generally, depending on which ion you're talking about.
But it sounds like bottom line, it's
difficult. It's difficult.
Really taste it.
It takes a lot of practice. Yeah, I don't know.
Well, it sounds like if you had a hard time, I don't know how any of us.
Yeah, would. I've not gotten to where I can taste the wort and add a little more calcium sulfate. No, I'm not there yet.
Okay. All right.
Great question.
I think we're done with that one.
Yeah.
Summarize. We've already answered that one, I think, and we've answered the next one. So, what is the best way to use the water book, the one you co-authored, to study?
Where is that?
For BJCP Cicerone. I've tried reading it but failed. And are there
very much sympathize
that
with
are
that.
more useful?
The Adjusting Water for Style, Chapter 7. That's a very useful chapter. That talks about how flavors and ions interact, and what you would do, in terms of adjusting, adding salts to achieve a particular result. So adjusting water for style, chapter 7. Also the controlling alkalinity chapter, chapter 6. And then chapter 5 is residual alkalinity and mash pH. That's like chapter 5 is your kind of science chapter. That's your required reading to do your homework kind of chapter. It explains these concepts. Chapter 6 gets a bit more practical and says, okay, now that you understand what residual alkalinity is, we're going to talk about how to actively control it. And that's chapter 6, controlling alkalinity. There it is. And then, so that's mainly pre-boiling, lime softening, acid additions, acid neutralization of alkalinity, and then chapter 7, salt additions for water adjustment. So those 3 chapters are really the nugget for water adjustment.
Well, great question, Ashley. I think we've got time for maybe one more, and I think it dovetails nicely into what you've done, John. pH is central for brewing, but measuring it seems inaccurate at best. I own a cheap pH meter. I think it works okay, but verifying that its accuracy seems expensive. pH papers seem not to have enough resolution.
They don't.
So is there a cost-effective pH measuring process or device you could recommend for the home brewer preparing for his BJCP written exam or similar?
The best solution is a good pH meter, a digital pH meter, 2 decimal point resolution. Should cost you about $100 US. Several models available from various manufacturers, but $100 gets you a good one. $400 you don't need. That's laboratory standard and benchtop and so on. $100 handheld pH meter will really do the job for you. It will last a couple of years. They're fairly easy to calibrate. They've got 2-point calibration. Just push a button, dip it in pH 4 buffer, dip it in pH 7 buffer. You're calibrated. That's really the only good solution to that question.
Well, I think knowing that the $20 ones and the $400 ones aren't the way to go.
No.
I mean, you've answered a huge question. I think our time is short, and I would like it to end gracefully. First of all, John, what a fantastic webinar! I can't go through all the points, but I like one that Gary Sane said. I've got 40 years in water treatment, waste, drinking water, high purity, along with reading water several times, and this